Okay. Thank you so much for having me. It is super exciting to be here. It's a huge honor to be a fellow, and this has certainly been an incredible learning experience for me. I'm a developmental psychologist by training, so a lot of what you all do in computational modeling is very out of field for me, but it is a great experience getting to stretch my brain here. So thank you for that. So today we're going to talk about skills and visuomotor skills in the wild, but really the subtitle of this talk is "It's Not Easy or Glamorous." You can see in this image, we are crouched on the floor around a sweaty child at an outdoor summer camp right next to a bathroom. And that's the way that you have to get it done sometimes in order to meet people where they're at in the community. It's great to bring people into the lab and get all these excellent, rich data sets and high fidelity measures. But at the same time, we can't only do that kind of science. We have to get out in the world and do the things that are happening in the community and make sure that we have person-centered and community-engaged research as well. So that's really the perspective that we come from in my lab. You're going to hear me use identity-first language during this talk for autism. This is in response to community feedback and also best practice published guidelines that are referenced here in case you're curious. If you want to talk about it afterward, I'm totally happy to, but I like to just offer a disclaimer because it can be a little off-putting for people if you've come through a training background that emphasizes person-centered language. So I do want to start off on the same page about what autism is and is not. It's a complex set of neurobiological differences. It's not just social, it's not just psychological. We know now it really is a whole body condition. And it's also not just a two-dimensional spectrum, low to high. The first thing students get told when they come into my lab is that low and high functioning are dirty words. We don't like to talk about autism in that way because the reality is that disability is context dependent. Disability can change for a person from day to day, depending on their environment, the supports they have in place, et cetera. And so really what we want to be thinking about is the whole person and the way that their cognitive capacities, their sensory capacities, and their physical capacities all interact to produce what we see as exterior behaviors. So it's important to think about the fact that no two autistic people look the same. The saying in the community is, if you've met one person with autism, good, some of you know you've met one person with autism. All right, so that's the way we want to think about this. One thing I want you to walk away with is this idea that maybe the things that we think of as canonical core features of autism are not the only things we should attend to. If we only focus on genetics and we only focus on brain and we only focus on social communication, we miss a larger piece of the puzzle. And really what we know is that in autism, there are lifespan motor problems all the way from cradle to grave. What happens is we get this emphasis, and the colors reflect this here, heavy emphasis on early childhood research, heavy emphasis on meeting developmental milestones, sitting, crawling, walking. And then we make sure they can do handwriting in school. And then we say, okay, you got it, go ahead. And we expect that they will just go through the rest of life without needing additional support. But the reality is autistic children grow up to be autistic teens, grow up to be autistic adults, and hopefully grow to be autistic older adults. And we need to understand that aging process across the lifespan. So that's really our emphasis in my lab. We know that about 90% of autistic people have motor difficulties. And in our studies, the way that we assess this was against the clinical gold standard assessments for developmental coordination disorders. That's the movement ABC and the DCD-Q, which is a caregiver report. 90% of our participants met the criteria. Only 48% of autistic people in the US receive OT though, and most of them receive it just for handwriting in school. Even smaller, only 19% receive physical therapy, PT. We're getting smaller and smaller in terms of resource access for a very clear and ubiquitous problem in this community. And only 1% of autistic people get a co-occurring motor diagnosis. Some of you who work in healthcare can understand the barrier that that's going to present for them when it comes to seeking support, clinical services, rehabilitation, things like that, because a lot of that is billing code driven, unfortunately. And if you don't have a diagnostic code where motor is somewhere in the definition, we're good. Carry on, OPA. If we're not in a setting where our clinicians can respect that and our insurance companies will, sort of eventually fold and let us have what we need, then we've got this massive barrier to care, all because we left this 89% out in the cold without a label that would have opened all of these doors for them. So one of the things that we really emphasize is that it's important to give people some kind of clinical coding that allows them to have access to that while we're trying to figure out the etiology, while we're trying to understand what the mechanism is underneath. So one of the core questions that we asked is this autism plus developmental coordination disorder? Is it that 90% of autistic people also have co-occurring DCD? Maybe this is what our data say about the clinical characteristics, the behavioral level output, but it may not be the case that 90% of autistic people have the same underlying mechanism driving their motor problems. Movement is complex. So it could be that we have some whose issues with movement are driven by visual dependence and their ability to process and integrate visual information. It may be that some have underlying vestibular disorders. It may be that some have attentional issues that helps or hinders their performance. And so we really need to get at that mechanistically, not just get stuck at the level of the observable behaviors we have in these sort of pass-fail clinical assessments. So the problem, though, is that this is visuomotor integration. Don't worry, don't try to read the whole thing. That's not the point. This is the point, right? The point is we have this big old tangle of Christmas lights of all of these networks that are interconnected and all of these different modules where things could go right or wrong. And so as different fields of research, we're over here studying attention in autism, and over there studying posture in autism, and over here studying gesture in autism, and no one's talking to each other. I'll tell you what I told somebody earlier this afternoon, that when I started going to INSAR, which is the big international autism meeting, the only motor things were me, my postdoc mentor, and 2 other people in posters in the back corner on the very last session of the very last day. No interest at all. Now we have whole symposia. So slowly but surely we're gaining some traction, but it means that we from this room have to go into that field. We can't wait for people in fields of these different clinical populations to come to us. We've got to go collaborate. So the challenges related to neurorehabilitation are pretty complex. We have a lot of unexplained variability across different conditions. We don't really know what the overlap is between those conditions. And then we have some challenges translating our methods from the lab to the community. I may not hit James's words per minute, but we're going to get pretty close here. I have to speed up a little bit. So the consequences of those unaddressed problems are that we have poor postural control, which, as you know, jeopardizes physical safety, puts you at risk for limited mobility, falls, et cetera, et cetera. And in our data set from Michigan Medicine, we see that autistic young adults are falling 12 times more often and needing clinical care for it relative to neurotypical adults, which is really striking. So in our studies, the way that we try to assess that is we have this VR paradigm where you are a user-controlled object and you have to move your body in response to different targets. The things we're going to fly through quick are published. They're QR codes. So if I go too fast, you're welcome to go and take a look in more detail there, or we can talk about it after. But the basic finding here is that even when they're able to perform a task, autistic people have difficulty with the efficiency of their task performance. Their path lengths are longer. They take a less efficient route to get to targets. Their movements are more languid when they're following a dynamic target, indicating that they're having difficulty integrating information about visual motion and staying on top of a changing trajectory of speed. So they're struggling there, and they're separable from people with developmental coordination disorder on these types of tasks. So here we get that nice separation between neurotypicality, DCD, and autism. So this is an indication that yes, there is something mechanistic that's a little bit different. We see the same thing when we look at jerk. Autistic people moving to a static target have higher jerk compared to neurotypical people. So again, we're getting at this idea that there's got to be something underneath in motor that we can eventually get to that's going to give us useful high yield information that will be sensitive and also specific. So how has computational modeling supported our work? I would be just lost in the library without my collaborators in engineering and in biomechanics and in computer science. And so they have helped us a lot with data integration, with data analysis, and with identifying specific visuomotor signatures of autism and of DCD so far. And so what we're working on right now, let's see if I can get this to trigger correctly. There we go. What we're working on right now is we've trained a computer vision algorithm to look at our eye tracking data. We collect mobile eye tracking on our participants while they move, and computer vision goes through and identifies objects of interest that we've trained it to, and finds them and tells us where they are in real coordinate space. So now we can look at the relationship between the vector of gaze and where the head is and where the body is and where the feet are in space, in conjunction with our full body motion capture data and our force plate data, which is really great. And all of this is on GitHub. If you want to play with it, you're more than welcome to. We're still refining it, but it's out there for you. And the goal here is to be able to get multiple data streams that help us unpack that tangled up string of lights, that help us see the different mechanisms that might be at play all within this one task or this one system, instead of only measuring movement in isolation. So in the wild, we do this at summer camps with a force plate where we can do some quiet standing tasks. We do mobile eye tracking in conjunction with that. And what we see is differences in postural control. So here you can see on the top in gray, someone who's typically developing, and on the bottom in green, someone who's autistic, just doing quiet standing with eyes open, eyes closed, and standing with their head in a dome for some sensory conflict. And what we find here that's really exciting for me is 95% of autistic people have tolerated this paradigm. And this is people from age 2 all the way up to 69. That's awesome to me because we don't have that many paradigms for assessment of motor that can span that age range, particularly in a population notorious for being a little wary of novelty and sensory sensitivity. So we're doing this in partnership with Special Olympics of Michigan and Special Olympics International, and we're going to different events and we're collecting these types of postural control data across their body of participants who are neurodivergent, sort of broadly defined, some with autism, some with ADHD, some who have intellectual disability. And they're doing this limits of stability task as well, where we ask them to move to a static target in different eccentric directions, and we track their path length to see how efficient they are. And what we've started doing recently is videotaping those movements so that we can run open pose on them and take a look at pose estimation while they're doing this as well, in conjunction with the force plate and eye tracking data. And it works great, mostly. The one thing that we are still struggling with is we really want to get this to where you can do it truly in the wild, where we're not having to over control settings of the situation just to make the model work. So you can see it looks at feet and it finds shoes and it says, oh, feet, and it tries to put something there. So we want to pay attention to this and make sure that we have a good paradigm that we can hand off to community members, clinicians, families, people in schools, and make this a really robust way of assessment. But I'll tell you from my own house, this is my kid in my house, by the way, you can get pretty good data from daily living tasks in your own home environment with this type of approach. And yes, it's not going to give you the same level of kinematic spatial accuracy as you would get from marker-based motion capture in the lab, but it is going to give us useful information as a starting point for understanding how these things are reflected in daily life in the natural environment. I know, I'm sorry. So the key opportunity and challenge that I see is we really need some standardized protocols. We have to have agreement across the field so that we can harmonize data, so that we can put data together from different groups transdiagnostically, but also across different types of tasks to get at these mechanisms. And that'll help us make our modeling more sophisticated. We also need transdiagnostic big data sets, which I'm delighted to tell you we have launched a project called Combine. It's combinedata.org, which is for motor behavior data internationally for sharing if you're doing standardized clinical assessments. And then what we're working on right now is, hang on, I don't want to do that one. I want to do this one as the last one. We're working on developing and validating a visuomotor integration score. So we are getting data from our open pose videos, from our force plate, and from our eye tracker, feeding all of this into an algorithm that would give us clinically relevant information about somebody's level of difficulty with vision, with movement, and with the integration of those two, normed by age, accounting for different physical characteristics. So that's where we're at the moment. So I'm so excited to be here and to share this with you. I know this is a little less modelly than everything else you have heard of, but I say it to you as a pitch because people like me need people like you to come and tell us all of the different sophisticated modeling tools that could help to augment and improve this work. Thank you so much.